In the Fermi gas model of the nucleus, it is assumed that the nuclear potential is approximately similar to that of a three-dimensional square well potential. If that is the case, then the neutrons and the protons inside the nucleus will arrange themselves in energy levels which are allowed in that kind of a three-dimensional potential well. Now, in the ground state of such kind of a three-dimensional potential well, the neutrons and protons will try to occupy energy levels so that the energy configuration of such a system is minimum. In such a case, the energy level of the highest occupied state minus the energy level of the lowest occupied state is known as the Fermi energy of that given system. Now, in this video, I'm not going to discuss the nuances of the Fermi gas model itself. I'll discuss the assumptions and the successes of the Fermi gas model in another video. In this video, I am more interested in calculating the Fermi energy of a typical nucleus by assuming that the nuclear potential is similar to the three-dimensional potential well. So let's begin. So as you already know, for a one-dimensional square well potential, which has a shape of this manner, then the solutions of the Schrodinger's equations gives a wave function which has the form a sine kx plus b cos kx. Okay, and the energy levels are quantized and have a form of n square pi square h cross square by 2 m l square, where L is the width of this kind of a potential well and En basically represents the quantized energy levels. So basically all kinds of a continuous distribution of energy levels is not possible. The particles stuck in this kind of a square well potential will only be present in those energy levels which are allowed by this expression, where n represents some integral value like 1, 2, 3, 4. And this expression can also be written as h cross square by 2m k square, where k is nothing but n pi by l. So k is the wave number, or basically it is the wave number of the wave correspond to the particle which is stuck in that kind of an energy level. Similarly, for a three-dimensional potential well or a three-dimensional square well potential, you have a potential structure which exists in three-dimensional space. Let's suppose the square well potential has lengths of Lx, length of Ly, and length of Lz in the axes of x, y, z respectively. Okay, so let's suppose this kind of a potential well in three dimensions do not have the same length in all different axes. They are Lx, Ly, and Lz. In that case, the energy levels of such kind of a three-dimensional potential well is given by pi square h cross square by 2m nx square by lx square plus ny square by ly square plus nz square by lz square. In the similar fashion that in the one-dimensional square well potential you had a quantum number n which can take values of 1, 2, 3 and on, which will determine the total energy. In the three-dimensional potential well you have a quantum number nx, ny and nz which is associated with this three-dimensional potential corresponding to x, y, z axes or directions respectively. So nx, ny and z can also take integral values. This can further be simplified by writing as h cross square by 2m kx square plus ky square plus kz square, where kx, ky, kz is the wave number associated with the wave in the x, y and z axes respectively, where kx is nothing but nx pi by lx, ky is nothing but ny pi by ly, and kz is nothing but nz pi by lz. Now kx, ky and kz are the wave numbers in three distinct axes. We can represent this as one distinct wave number. Let's suppose we write this as h cross square k square by 2m, where k square is nothing but kx square plus ky square plus kz square. So this is the energy allowed in the three-dimensional potential well, and only those energy levels will exist which is allowed by this kind of an expression where nx, ny, nz can have integral values. So now nx, ny and nz can have values of 1, 2, 3 and other integers, 1, 2, 3 other integers, 1, 2, 3 and so on and so forth. So basically you can have an energy level of nx, ny, nz having values 1, 1, 1 or 1, 2, 1 or 2, 1, 2 or 3, 1, 3. Any kind of a combination of nx, ny, nz out of these allowed integral values will correspond to some distinct energy level in this kind of a three-dimensional potential well. So similarly, since I'm writing in terms of the wave number, I can have energy levels which are distinct and existing for wave number values of 1 pi by Lx, 2 pi by Lx, 3 pi by Lx and so on and so forth, and ky being 1 pi by Ly, 2 pi by Ly and 3 pi by Ly and so on and so forth, and kz being 1 pi by Lz, 2 pi by Lz and 3 pi by Lz and on. So any kind of values like pi by Lx, pi by Ly, pi by Lz or some other combination of these numbers will yield a distinct possible energy level in a three-dimensional potential well. If we take the three-dimensional coordinate axes of x, y, z and then we try to draw a three-dimensional space where x, y and z are replaced by kx, ky, kz, then in that case the allowed values of kx, ky, kz will represent a particular point in 3D space which corresponds to a distinct allowed energy in the three-dimensional potential well. So let's try to draw that kind of a three-dimensional space and infer from information from there which can help us calculate the Fermi energy. Here I have drawn the three-dimensional coordinate axis, but instead of having x, y, z axis, I'm representing the kx, ky and kz axes respectively. And since kx, ky, kz cannot have any random value but rather only those values which correspond to integral values of nx, ny and nz, so these points here, the blue points, represent those allowed values. So in the kx axis you will have this first blue point representing pi by Lx value, the second blue point representing 2 pi by Lx value, and the third blue point representing 3 pi by Lx value, and on and on. Similarly, in the ky axis, the first blue point represents pi by Ly, the second blue point represents 2 pi by Ly, the third blue point represents 3 pi by Ly, and so on. And similarly also in the kz axis you have pi by Lz, 2 pi by Lz and so on and so forth. So basically these blue points, they represent a unique allowed value of kx, ky and kz, and if you join all of these blue points with perpendicular lines, then you will get a sort of a grid kind of a structure consisting of large number of boxes which will look similar to this. So this entire space which is distinguished by kx, ky and kz axis, or let's say this is the k space, this entire space will be filled with these kind of boxes in which the intersection points of these boxes or the will be basically representing a distinct kx, ky and kz values which are allowed. So out of this grid, if I take one box out of it, you will realize that each individual endpoint or the intersection point represents allowed value of kx, ky, kz. So basically this is the kx axis, this represents the ky axis, and this represents the kz axis, and these points represent the allowed values of kx, ky and kz. And since they represent the allowed values of kx, ky and kz, they will also represent a unique energy state. Since as I just now showed, the distinct energy levels or energy states correspond to allowed values of kx, ky and kz. So these blue points which represent allowed values of kx, ky and kz will also represent distinct energy states. Now if you look at this particular box, what is the length in the kx axis? The length in the kx axis is nothing but pi by Lx. Yes, because there is a difference of pi by Lx between each of these points in the kx axis. And what is the length in the ky axis? It is pi by Ly. And what is the length in the kz axis? It is pi by Lz. Then what is the volume of this individual, let's suppose a unit cell, okay? So if I say that this is a unit cell, then the volume of the unit cell in the k space would simply be equal to pi by Lx multiplied by pi by Ly multiplied by pi by Lz, which is equal to pi cube by Lx Ly, Lz. Now please remember that Lx, Ly, Lz by my definition are the lengths of the square well potential. So Lx, Ly, Lz basically represents the volume of the square well potential that I have defined. So then this becomes pi cube by V, where V is the volume of the potential. So if I represent kx, ky, kz in some kind of a k space which looks like this, then you will end up getting a grid system consisting of a large number of unit cells, and the volume of each unit cell will be pi cube by capital V. Now as I just now told you, each of these blue points represents a unique combination of kx, ky and kz which is allowed, and therefore they also represent a unique energy eigenstate. So how many energy eigenstates are there in one unit cell? So if you look at the unit cell, you can count 1, 2, 3, 4, 5, 6, 7, 8. So for each unit cell, there are how many number of intersection points? There are 8 intersection points. So they will correspond to how many distinct energy eigenstates? They will correspond to 8 distinct energy eigenstates. However, you might just realize that each of these points do not just belong to this one unit cell, but rather it also belongs to its nearest neighbors. So for example, this particular unit's blue dot, which represents some distinct energy state. So there are going to be 8 nearest neighbors, 1, 2, 3, 4, and in the front another 4. Total 8 unit cells will share each of these blue dots. So basically each energy state is being shared by 8 unit cells. So for each unit cell, it has 8 distinct energy states, and each of these distinct energy states is being shared by nearest 8 neighboring unit cells. So the net effect is that each unit cell will uniquely correspond to a total number of 8 multiplied by 1 by 8 energy eigenstates, which is equal to 1. So the net effect is that one unit cell will uniquely correspond to a 1 energy eigenstate. And I can also say that in 3-dimensional case space, a volume of one unit cell will correspond to 1 distinct energy eigenstate. So if some kind of a potential has, let's suppose, n number of energy levels which are occupied, and I represent those occupied energy states in k space, then they will correspond to points which are spread out in a region, and the volume of that region will be basically volume of each individual cell multiplied by the n number of energy eigenstates. So let's take this argument forward. Let's suppose in a typical nucleus, there are n number of particles. Now the potential for a neutron as well as a proton is different from each other. They are distinct from each other because neutrons and protons are distinct particles, and they also experience different forces. The protons experience Coulombic forces, so the potential for the protons will be a little bit different. So for any one type of this particle, if they are organizing themselves in some energy levels, since neutrons and protons are fermions, so 2 particles can occupy one distinct state. There are n number of neutrons, and since 2 neutrons can occupy one distinct energy states, therefore there are going to be n by 2 number of distinct energy states. And if I represent n by 2 number of distinct energy states in k space, then what is the volume in k space that is going to be occupied by occupied energy states here? It's quite simple. The volume of one occupied energy state is given by pi cube by capital V, and since there are n particles and 2 particles occupy one distinct energy state, then there are going to be n by 2 number of energy states. So we multiply it by n by 2, then this is the volume of occupied energy states in k space. So the volume of the occupied energy states in k space will be given by this. Now you might be wondering, what is this red line? This red line simply represents the surface of a sphere. It represents that boundary which distinguishes the occupied states from the unoccupied states which are lying inside. So if you imagine this as a 3-dimensional surface, so think of as a sphere which is centered at the origin. Now since kx, ky, kz cannot have negative values, so only the first quadrant is occupied, and the first quadrant has those states which are possible. But if I try to distinguish the occupied states from the unoccupied states, in that case I will end up getting a spherical surface. Why do I get a spherical surface? Because you might remember from my calculations, the wave number k square is equal to kx square plus ky square plus kz square. So this is the equation of a surface sphere basically. So if you take all the distinct values of kx, ky and kz, then the highest energy state will have a large number of degenerate energy levels which will fall on this particular surface, which is also known as the Fermi surface. So the volume of the occupied states is basically this much. Now we can also say that this kind of a Fermi surface distinguishes the occupied states from the unoccupied states. And if the Fermi surface, which is basically part of a sphere, has a radius of, let's suppose, some value kf. Okay, kf represents the radius of this kind of a Fermi surface, which distinguishes or which divides the occupied states from the unoccupied states. In that case, the volume of the occupied states simply be volume of the sphere multiplied by 1/8, isn't it? Since this is 1/8 of a sphere, so 1/8 of a sphere having a radius kf, is this the volume of this kind of a sphere in first quadrant, which is nothing but the volume of the occupied state. So this is equal to this. So then 2 and 4 gets cancelled, pi and pi square is left. You end up getting kf is equal to, kf cube is equal to n by v 3 pi square. Now in this case, n is the number of neutrons and v is the volume of the potential. So n by v can simply be referred to as the mass density of the neutrons. So n by v can be referred to as the mass density, or the density basically of the neutrons and how it distributes itself in the potential volume. So the kf is now basically 3 pi square rho to the power 1/3. So this is what you can say as the radius of the Fermi surface. So if this is the radius of the Fermi surface, using this expression we can find out the highest occupied state. So the highest occupied state will basically correspond to the Fermi energy in this case. So the Fermi energy therefore becomes, using our original expression, the Fermi energy EF is equal to h square kf square by 2m. So this is the original expression where kf is nothing but the wave number associated with kx, ky and kz, the highest occupied combination. So kf represents the highest occupied magnitude of the combinations of kx, ky and kz. So this therefore becomes h cross square by 2m 3 pi square rho by 1/3. This is the Fermi energy, or approximately the Fermi energy of a square well potential which contains n number of neutrons. So to calculate the Fermi energy for neutrons, first we will just use rho is equal to n by v, where n is nothing but the number of neutrons in a given nucleus. Now usually you will find that the number of neutrons and protons follow what is known as the NZ graph, and for smaller nuclei the number of neutrons and number of protons are distributed 50-50. For medium sized nuclei the number of neutrons starts exceeding the number of protons. So if you look at the medium sized to large nuclei, you will usually find that the number of neutrons are almost 60% the total number of particles. So I'm going to use that expression. So the number of neutrons are almost 60% the total number of particles, which is the mass number, and the volume is 4/3 pi r cube, where r is nothing but r is equal to r naught a to the power 1/3. So this is going to become 0.6 a by 4/3 pi r naught cube a gets cancelled. Okay, if I replace this in my earlier expression, EF is equal to h cross square by 2m 3 pi 0.6 into 4/3 pi r naught cube square to the power 1/3. If I put all the values, the mass of the neutron, the Planck's constant divided by 2 pi, pi r naught is 1.1 femtometers. If I put up all the values according to my calculations, the Fermi energy for the neutrons comes out to be around 43 or approximately 43 mega electron volts. So based on whether or not you take 60% or 50% or 55% the number of neutrons in a nucleus, you will get a little bit of variation in the Fermi level, Fermi energy. But for according to my calculation, the Fermi energy comes out to be 43 mega electron volts for the neutron potential well. If for the case of protons, however, if the neutrons in a large nuclei is 60%, the protons are going to be 40%. So if you put up the values for protons, the proton density will be 0.0 4a divided by 4 by 3 pi r cube. If you put up this expression and then plug in all the values, then the proton energy level comes out, proton Fermi energy comes out to be around 33 mega electron volts. So these are the Fermi energies of the ground state configuration of neutrons as well as protons, by assuming that the nuclear potential approximates a three-dimensional square well potential.